Hi all, my name is Dhruv Sharma and I welcome you all on our new session on route tags with OSPF. In this session, we will discuss about what are routing tags and how we can efficiently use them to overcome some network issues. On that note, let's jump in. Route tags are basically used to avoid routing loops within OSPF or I would say any routing algorithm. Usually, any distant vector routing protocol will use split horizon to avoid routing loops. But these routing, these route tags are bit little different. These are used in a scenario when we have two routers, they're connected, and one router is basically advertising a different routing algorithm like RIP or EIGRP on the one end and on the OSPF on the other end. So we often have such situation where we have to redistribute RIP routes into OSPF and OSPF route into RIP. And we can somehow land up in a situation where this redistribution can cause a routing loop. In this session, we will explain you how we can end up into a routing loop situation and how we can overcome it. For the sake of this demo, we will be using this network topology. This network topology is built in my lab, and where we have R1 and R2, R3 and R4 routers. R1 is part of a RIP network protocol, and which is a distant vector protocol, and R4 is basically a link and R4 is associated with OSPF, which is a link state. R2 and R3 with respect to OSPF, they are ASBR. If you have any questions, what is ASBR? So you need to check with some Cisco online documentation to understand what is ASBR. But in a nutshell, ASBR, which is shown in an orange color in my diagram, is used as a border router where non-OSPF network is trying to communicate with an OSPF network. So in our case, it's a RIP is trying to advertise its own network into OSPF. That's why these routers are basically they are configured as a role of ASBR. So in our before we get into understanding about those routing loops, let's do some. I will explain you how my lab is currently built in. So as we can see, R1, R2, and R3 on their north end, they are configured with RIP. R3 can reach R2.2.2.0 via F0 network over RIP. And R3 can reach 1.0.0.0 network via F10 via OSPF. So similarly, it lies true for R2 and R2 as well. So R2 can reach 2.2.0 via RIP over this interface, and it can reach 1.1.1.1 via south side interface. We haven't started with redistribution yet, so everything is working fine, but now there is a need to redistribute 2.2.2.0 network into OSPF. But now it's a bit tricky. Now, as we know, RIP and OSPF, is preferred over RIP. So now what happens if I go on R2 and I try to redistribute 2.2.2.0 into OSPF? Let's see. So R2 and R3. So this is their configuration for reference. As we can see, the network topology stands true. You can access these slides over the link in the description. We can see R2 and R3. The routes for 2.2.0 is available over the RIP, and 1.0 is available over the OSPF. Similarly for R3. R1 is a pure RIP router and R4 is a pure OSPF router. But now, as I mentioned, what happened, we now redistributed 2.2.2.0 via only R2 using this simple command. This is a CLI for reference. As soon as we redistributed R2 into OSPF, this route 2.2.2.0 is advertised within OSPF. And as per the algorithm, all the external routes will be redistributed into OSPF as E2 routes. If you have any questions about what are even and E2 routes, I would highly suggest you to review some Cisco documents online. So 2.2.2.0 is redistributed into OSPF, and now the most important aspect I would like to explain you. As I mentioned, R3 before redistribution can reach 2.2.0 via RIP. So there was supposed to be a routing entry which says routing protocol is RIP. It can reach 2.network via F0/0 interface. But now, as soon as this network is redistributed, R3 will prefer to reach 2.2.20 via OSPF because administrative distance of OSPF is preferred over RIP. So rather than going through the north side to reach 2.2.2.0, R3 will take a longer route via R4 and R2 to connect to 2.2.0. Whereas previously via RIP, it was connecting via directly to R1 over RIP. But now, since R2 has already redistributed 2.2.0 and OSPF is a higher preferred routing protocol because of lower administrative distance, it is preferred. So this is a screenshot which I have captured. This is a screenshot pre-change and this is post-change. In pre-change, we can see 2.0.0 network, which is basically the network behind R1. R3 before we redistributed 2.0 into OSPF, it was showing it via 10.10.10.10. But now it is available via 11.11.11.12, which is IP address of R4. So with this redistribution, R3 will going to take a longer path. Yeah. So now we will discuss about. So far, let me just try to summarize what we have discussed so far. We haven't did anything much. We are R1, R2, and R3 and R4. They were R1 is part of a RIP network. R2 and R3 on the north side, they are part of they join the RIP family. And on the south side, they join the OSPF family. Everything is working fine. We have only redistributed 2.2.2 network into OSPF. The command is here, and R2, R3, and I've shown their routing outputs in my previous slides. The only disadvantage what I felt so far is R3 have to take a longer route to reach 2.2.2. network via OSPF. But that is still not a problem. But problem happens. So this is a catch, guys. You have to understand this very carefully. If you have any questions, do not hesitate to contact me. The problem happens only when if someone by mistake, or someone by purpose or mistake, what I would say, configure R3 as an ASBR, and and the route what R2 has advertised, which is 2.2.2.0, and R3 can see it in its routing table, it redistributes the same network into RIP. See, let me revise whatever I just mentioned. Initially, what we did, R2 redistributed 2.2.0 network into OSPF using this command. Now, this topology is very simple. We just have 4 routers. It's not a big topology, easy to track. But imagine it is a big LAN network, and someone on R3 run a command that any router, all the OSPF network are automatically redistributed into RIP. So if this command is run over R3, it will cause a routing loop, and I will explain you how. So as I mentioned initially, as soon as the OSPF was redistributed, this route was deleted and it was replaced by OSPF. And what we did, we redistributed this network back into RIP. This network was initially learned by a RIP, but now because someone didn't notice it that we have already learning route from RIP, they redistributed the OSPF into RIP again. And now when R1 will receive an update that there's this router R3 is showing a route of 2.2.0 network. Now the routing table, let's see the routing table of R1 will look like. It will show that R1 has a route for 2.0 northbound, and it will show that if in case we configure that R3 is also showing a route for 2.0 network with a higher metric. Let's say if I redistribute this RIP network, this same network what I've learned from OSPF into RIP with a higher metric. So R1 will delete its route which it originally learned, and it will replace the route pointing towards R3. So I will revisit it again. So what happens? What happens? R1 initially R2 from R2 basically redistributed this network into OSPF, and when this route reached back to R3 via OSPF, we redistributed the same network, 2 dot network, back into OSPF, back into RIP again, pardon me. And when this redistribution happened, somehow we increase the matrix size, matrix size to maybe 1 or 2 something. And when this route reaches back to R1, and R1 see that, hey, I have a new route available to reach 2.2 network with a better preferred metric value, R1 will delete its original network destination what it reached earlier, and it will replace the route which it learned from R3. and this will cause a routing loop. Oops. I will get back to my slides. So this is the configuration of R1. Now what we did, we redistributed R3 routes into all the R3 is configured to redistribute everything into RIP. So this is the output now. As we can see, R1 now has route for 2.0 network. So this is a pre-change, and this is a post-change. So with the post-change, R1, which is the northbound RIP only router, which earlier had 2. Network connectivity directly to it, but now it sees an entry via 10.10.10.11, which is nothing but R3 with a higher metric, because when we redistributed it, we basically give a redistribute command with a higher metric. This I again mentioned, with just 4 routers, this kind of mistake is very unlikely. But if it is there's a huge network, someone can easily do this mistake and configure another router. Ideally, there should be a one single router which should perform. We should own an ASBR role for RIP and OSPF, or EIGRP and OSPF, and it should perform uh, redistribution across, not two routers. In our case, someone ideally R2 should be configured to redistribute RIP routes into OSPF and OSPF routes into RIP. But in our case, someone configured R3 to redistribute OSPF routes into RIP and RIP routes into OSPF as well. So we can configure that as well. But with this, uh, it will cause a routing loop, because right now R1 is basically confused that 2.0.0 network can be reached via two different instances. But how can we fix it? I hope by now it's clear that we are in a bit of a mess, because R1 will delete is likely to delete any route for 2.0 network if it finds another entry to reach 2. Network with a with a lower met or with a lower with a high preference route. So it will delete this entry that I can no longer reach. It will delete the entry to reach this 2.0 network via F2.F2/0, and it will say that this 2.0 network can be reached via RIP, and RIP will send that the traffic is reached via R4, and R4 will say that the traffic is reached via R2, and R2 will say that yes, I am still advertising the route, and I am getting the route via R1, but R1 say that I am still getting the route via R3. So R2 will still get the route advertised into RIP, because R1 say that I'm still having this route available on me, not via F2/0, but via R3. So this creates a complete routing loop. This is very easy to fix it, and I will explain you how to do it. And the easy way to fix it is via route tags. So route tags. So let me quickly explain this, how route tags will basically be helpful in setting up this information. If you have any questions so far regarding how this redistribution happened, I will highly recommend you to check online, go through some Cisco articles, Cisco documentation, and they can easily explain you how this redistribution happens. You can go through these outputs of these of this of the routers over the slide, and the slide is mentioned. The access to the slide is mentioned in my description. Okay, so yeah, so over here we can see that to fix this routing, now we need to ensure that any routes. So to fix this routing loop, we just need to ensure that to to, to let R3 confirm that any route. How we how we do that. When R2 redistribute any route like from RIP into OSPF, uh, it will add a tag, and you can give a name like tag1. And when R3 will try to redistribute the same network into RIP again, if it see that tag, it will skip the redistribution. It's pretty simple, right? So we just have to stop this 2.0 redistribution into RIP just by tag. Simple, isn't it? And we can view the tag by show IP route and the network name, and we can see what is there any tag associated or not. It is very simple. So before we get into, well, let's discuss about what are route tags. Route tags are nothing but the numbers, and we basically define route tags on the ASBR. So if I go back, typically this is our ASBR, which is designated or configured to redistribute RIP routes into OSPF. And yes, and what we'll do, we'll go back to the R2 configuration. We will configure a route map. We can call it as a tag. We can call it as Dhruv. Give any name, and we define we deny. We add a deny rule and tag deny rule 10 and match a tag value which is 1. We'll again create a route map tag with permit 20 and set a tag value as 1. We'll go back into OSPF configuration, redistribute route map uh, against that RIP configuration. We will add a route map and tag, and followed by the network configuration. Similarly, within the RIP, we can even again, this is optional, but if you want to have that extra security of routing loops, I would highly recommend to configure RIP routes into OSPF and map the same route tag. So what happens? What exactly this route tag does? When with the sequence number 10, it says that if anything that matches tag 1, deny it. And the second, then this one, what it means that with sequence number 20 says that we need to set everything to tag 1, because right over here we didn't had any match condition. With no match condition, it means everything to match. So all the traffic will be set to tag 1, and once the traffic is tagged to tag 1, it will be denied. So what I mentioned, what it means that over here we will configure some tags, whatever routes it will learn from from RIP to OSPF, everything will be tagged to tag 1. And when this tag 1 is carried over to R3, and we can see this tag 1 over here, it will see that if this route, since this tag parameters are cascaded within the OSPF, and with the OSPF update, if you see that tag 1 is associated with the configuration of deny, it will not redistribute this network back into RIP. So it is important that first you need to create two route maps, one with the deny statement, another with the permit statement. If anything that matches tag 1 will be denied, and if there is no match statement, everything will be matched and everything will be mapped to tag 1. So R3 cannot skip or cannot bypass this rule. So anything which R2 has redistributed, R3 cannot redistribute it back into RIP. So verification, if I go back into R3, I can see that tag 1 is associated with the route number route 2.0.0.0, and finally it cannot, because tag 1 is displayed over here, it will not redistribute this network back into RIP. Similarly, R1, if we set up this command of router RIP, and when we redistribute OSPF route into RIP, and we mention the tag value on it on R2. So similarly, no one can do a mess of no one can basically do a mess of configuring such route map issues. So if we go back to R1, we can even see tag 1 associated with 1.0. So if R3 try to redistribute this network back into OSPF, it cannot do it. So what I mean, let me summarize again. This is 1, this is 2, this is 3, this is 4 router, for instance. Any route which is advertised from 1 into 2, R3 will do the job for us. And R3 will also help us to advertise anything what it learned from over here. But if in case someone by mistake try to configure R4 to redistribute the network, R4 cannot redistribute any network to and fro if it see a tag associated with it. T tag. In our case, the tag value is 1. So as soon as it see this router see that there is a tag value associated with it, it will stop redistributing the network. This is very important when we are basically working on a big topologies. So we have to ensure that there is a one ASBR who is redistributing the network, and one who's redistributing the network, which is in our case is this router. Is this R2 as a router? It needs to be ensured that routing tags are basically associated with all the routes which is redistributed from RIP to OSPF and any OSPF to RIP. Like tag 1 and tag 2 maybe, or tag 1 and tag 1. So number doesn't make a big difference. So whenever R3 is also trying to duplicate the effort of redistributing the routes again, whenever R3 will see the tags associated with these routes, it will stop performing its action. Nice and easy, isn't it? Quick tips. Routing tags when redistributing into BGP is not supported. RIP1 doesn't support route tagging. Yeah, in my previous example, we were basically redistributing the complete network. As we can see, we are redistributing complete RIP, and you can basically create an ACL and then match an IP. You can customize your route tags and distribution using route map and ACL, which is pretty simple. So you don't need to create this configuration, can be fine-tuned. So this is for the session, and I want to thank you for everyone joining, and I hope this session was useful. Thank you and have a nice day.